Welcome everyone
Hello.
back with yet another stream.
Wow.
When will they end?
Another week, another stream.
Another week, another stream. That's right. Hopefully people are seeing us live. Let me just double check.
It's always good to know.
We can't see the chat right now, but I think we are live.
I can check real quick.
Sure. Yeah, we are. I can see it.
Okay.
Sweet. All right, well, welcome everyone. Another stream. Today's a very, very exciting stream. We've got some very new types of 3D printing. We've got a special guest.
Yeah.
And, well, what are we going to be talking about today, Steven?
Well, we're going to be talking about the possibility of automating metal 3D printing. And we're going to compare that to different forms of manufacturing out there, such as CNC machining or forming, and yeah, just looking at pros and cons of all the different types of manufacturing out there. And yeah, we'll be having a special guest with us, one of our special customers, MachineCreators, also known as Jeff Parker. He'll be joining us. He does a lot of CNC work, and
So it's very convenient in a stream all about metal manufacturing to have.
yeah, it's almost like we chose him because he was good at CNC and
Almost.
also 3D printing.
Yeah.
So yeah, without further ado, Jeff,
Yeah.
welcome to the stream.
Throw him up.
Hey, how you guys doing? Thanks for having me today.
It's great to
Yeah.
see you.
Doing well. Excited to have you on. Super excited, actually. Yeah, I mean, we've been talking for a long time, but I think it'll be really great for everyone to hear your perspective, coming from your background. And why don't you just give everyone an intro, like what you do, what kind of stuff you work on, and a bit about yourself.
Yeah, so my name is Jeff Parker, and I've started a small business called MachineCreators, and I'm really passionate about building 3D printers and CNC machines, and it's something I've wanted to do for a long time. So being able to build that for other people and show them how to use them and get people trained up is that's really exciting to me.
And you have your background is in CNC machining originally before you got into 3D printing?
Well, my background, yeah, 3D printing for a little while, with CNC, and actually used 3D printers to rebuild the CNC machines and convert the machines in. So I've got a mill over here that I took from a hand crank mill, 3D printed parts to turn it into a CNC machine, and moved up from there. So I sent a video. You guys maybe can show a little bit of that. The most recent CNC machine I built was 5 foot by 10 foot, kind of a monster. If you want to pull that up.
Yeah, I'll throw it up on stream while you talk about it.
Okay, yeah, that was a pretty ambitious project for running out of my basement. I don't know if you guys have got shipments of 24-foot extruded aluminum before, but when it comes in a box that weighs 200 pounds, it's pretty hard to drag down there and cut up.
Yeah, usually ours is, I think we get ours in like 8-foot lengths.
Yeah, they come in pretty big wooden boxes, but the 24 is a bit longer than we usually go for.
I don't know how your residential delivery person felt about that.
What kind of like program does your CNC machine use? Like, just curious, kind of what design choices went into it.
So originally, I started out with Gerbil, which, if you're familiar with CNC in the hobby level or the 3D printers, the Marlin firmware is based off of it. And this machine actually runs off of Mach 4, but recently there's been a fork of Gerbil called Gerbil How, and it supports more modern 32-bit CPUs. So you got something like a Teensy controller. It's more like the modern 3D printers now.
Right. And that's cool. How like I'm just curious what made you go for a custom build like this?
Well, originally it was just a challenge. I wanted to see if I could do it and use the one 3D printer I had to see if I could make it work and design parts and build it. So for me, it's the challenge of building something, the discovery and research and design.
Yeah, right. The process is pretty like fun, if you can call it that. I know I've done a few custom builds before.
Sometimes.
Nothing as much as the CNC machine that you've done here, but yeah, a bit of fun, but a bit of probably hair pulling as well.
Yeah. That's why I grew extra hair, so I had more to pull out while working with 3D printers.
Yeah.
Right. And when you've only got one 3D printer, it's a bigger challenge. Now I've got all these automated Quinley systems behind me, and they're just constantly cranking out parts as fast as I can design them. It makes it a lot easier to build machines.
Yeah, you see you're printing out some stuff right now.
Yeah, I've actually, these are, I'm also getting into electronics, got a background in electrical engineering, so PCI Express brackets, so just tools to help me out around the shop or the lab.
Cool.
What are the main types of things that you've been printing now that you've been able to do higher volumes?
Probably the biggest volume part was I got a contract with a local museum called the Museum of Discovery. They have a program called Tinkerfest where hundreds of kids come in from all around the state and even out of state. They have activities set up, and it's a real blast for the kids. So the original contract I had 2 years ago, you know, the Mentos Coke challenge where you drop Mentos in and it shoots out a spray of foam.
Yeah.
Mm-hmm.
So imagine that times 200 kids doing it. Our 3D printed nozzles on build plates, 16 at a time, like days and days, cracking them off using glue sticks. Sorry, I didn't have a photo of that, but maybe I could find one for you.
We can imagine, I guess.
Yeah, I think everyone
This
watching.
year, with the Quinley system, I had 2 printers going. They wanted 400 paper airplane launchers. They're going to launch a bunch of paper airplanes off the top of a parking deck. And 48 hours of continuous printing, I had all 400 of them complete.
Wow, that's really good.
Yeah, I think we calculated that would be like the equivalent of doing 54,000 per year, which is like
That's pretty good.
I'm not doing that kind of volume continuously, but it is a pretty impressive number.
Yeah, yeah. I mean, I'm sure even like 40 would be pretty achievable with the current setup that you've got. But yeah, it was kind of a really impressive number to hear. Just 400 3D printed parts over the course of, a weekend or something.
Yeah, it's the kind of stuff we love to hear.
Yeah, yeah, for sure.
Yeah, there's a combination of batching and the 3DQ system.
Yeah,
That's what we found is best.
yeah, there's some clever ways, and actually, speaking of batching, that does kind of take us right into the main topic today, which is going to be talking about metal additive manufacturing, how that works, how that's been used to scale, or how that's been scaled, and also just regular metals fabrication, because batching, as you'll see, kind of as we talk through this, is it's going to be a really big theme. Um, and I think people know, like with plastic, that's already kind of that's a thing, but yeah, with metals, it's on a whole nother level.
Yeah, well, metals are, you don't think of metals as being a thing for, um, like makers to get their hands on, really. It's more like plastics and hand tools and stuff like that. But now with automation, it could actually be, um, like worth your while to get into metal. So, yeah.
Yeah, I was thinking about that earlier. If you print the part that would traditionally be made with something like an aluminum casting, right? That's your bulk of your part. And you get that, and then you take it to your finishing process on your CNC machine, so you've got high tolerance holes and surfaces.
Yeah, and that seems to be how a lot of metal 3D printing is used right now. So the right now the main the main places metals are used are in really high value, um, expensive, for very high value expensive parts, where it actually makes sense, because most metal 3D printers, that are used in industry cost between 50 and $50,000 and $2.5 million. Some are even in the tens of millions of dollars, especially as you try to push more volume. So you see it's been really strongly adopted by things like aerospace or the medical field, where you are doing lower volumes of critical, complicated, parts that you can afford to spend thousands of dollars on fabricating.
Yeah. Well, and also with additive metal, you can get sort of benefits that you can't really get from other processes. Like you can consolidate like hundreds of parts maybe into a single design
Mm-hmm.
and make it half the weight. And then in these kind of applications with aerospace, for example, like weight is a huge issue. And if you can save, 50%, that's pretty huge.
Yeah. And so one of the biggest problems with metals is that it's so inaccessible, and the companies that were able to adopt it are, when they're using metal additive, it's typically they have a lab specifically for using metal additive. They have a team of 5 or 10 people, a few of whom are specifically trained around using metal additive, and that works for them. They're able to invest, um, millions of dollars into a very specific setup, because for those high value parts and difficult to machine parts, metals and that the current cost of metals actually makes a lot of sense. It still saves you so much in terms of part cost, and as long as you're not really pushing volume, you're doing pretty well, because
Yeah.
low volume seems to be kind of the antithesis of CNC machining or other high volume metal, manufacturing technologies. Like one of them that's really big right now is metal injection molding, which is now being used alongside casting to kind of get the lower volume side of, or I should say, casting is used for extremely high volumes generally, or
Very low.
really expensive parts,
Yeah. You get like sand casting, which is like the opposite, where you get
really low.
really low volumes of like rough parts, for example.
Yeah.
Or you can get like die casting, which is like a lot more expensive.
And now you've got metal injection molding, which kind of hits the same volumes that injection molding does, which is, between tens of thousands and millions of parts, except the curve is a bit different, because metal injection molding is really expensive due to the wear. But yeah, where metal 3D printing has kind of fallen now is you can do really high volumes, but it's like if you look at all the examples of high volume metals, it's either somewhere in aerospace where they can afford to be making, you know, $300 parts at a quantity of 100,000, and it takes them a few years to get to that quantity. Um, or you see it with really, really small parts, and that's kind of where binder jetting technology from HP and Desktop Metal have found sort of a spot in the market where they can do huge batches of small kind of I don't know how you describe it, like just smaller parts in general.
Yeah, small but complicated, right?
Yeah.
And I guess they have these like really interesting arrays of parts where they just like batch like hundreds into a single build volume.
Yeah. And then the cost of that is directly inverse to the size of the part, and also your production throughput is directly inverse to the size as well, because with something like a binder jetting system, and this is even true for like selective laser sintering of metals, is the more parts you can fit into a single bed, the more parts, the more throughput you'll have.
Mm-hmm.
And that's because the time to print a full bed, especially with binder jetting, is essentially fixed. So because it always has to do a pass. With laser sintering, it's a little different, because if the laser has to take a longer path,
you've got like a single dot tracing the path rather than a whole 2D scan, or I guess line scanner.
Yeah, it does. The binder jet does a scan across everything. But regardless, these are the two highest volume metal printing technologies. And as a rule of thumb, it's sort of the more parts you can fit, the lower cost the part will be, and the more parts you'll be able to produce per year, because your volume is basically fixed time.
Mm-hmm.
And I think this has been, and we'll get into this, but I think this has been really limiting to metal 3D printing, because it's sort of being forced, in order to be affordable and scalable, you're either being forced to buy a bigger and bigger machine so you can fit more parts in your area, or you're forced to make your parts flatter and thinner and smaller so that you can pack more of them into the same space. And it kind of goes against the whole point of 3D printing, which is the ability to print any shape.
Design freedom.
Yeah.
It's getting more constrained now if you have these build volume limitations.
Yeah.
So why don't we, Jeff, why don't we ask you about, so how, we've been talking about how you do metal 3D printing. Say you wanted to produce a part with the CNC process. How would you go about like mass producing a part in CNC? Like, what are some things to consider?
Well, yeah, and I'll point to my background that I'm hobby CNC, so my mass production may not be the same as if you have a professional machine with auto loading of materials.
Yeah, that's understandable.
But from my perspective, I would go about designing a jig for your clamping. So when you're able to support that on your machine, you have a reproducible pattern, right? You run your G code and it's the same each time. And with the clamping systems for a hobbyist, you're really going to be limited to like a hand crank mill vise, and then you machine out your jigs that fit into that.
Yeah, right. So I guess a significant portion of work actually goes into the whole work holding solution, right?
Yeah, it's huge.
That's actually interesting. The people have started using 3D printing to cut down on the on like the complexity of that, right? Have you ever tried anything like that, 3D printing a jig?
I have made it through a few 3D printed jigs, and the great thing is when your bit cuts through it, it doesn't matter, right? If I tear it up, I can print another one in a few minutes, or however large it is. so it usually doesn't take too long.
I didn't consider
And
that. That's a nice.
I don't feel like I'm wasting material like I do when I'm making an aluminum work holding.
Right. And how much, like, when you are doing a CNC job, how much time would you say is spent on setting up the machine, setting up the work holding, like either a plate or system versus actually machining the parts? Like, in terms of, maybe let's break it down in terms of when you're designing your part, how much time are you spending thinking, how am I going to hold this part in the machine? And then when you're actually fabricating the parts, how much time do you spend fabricating, or would you typically spend fabricating the work holding jigs versus the parts themselves?
A lot of that depends on the volume. If I'm just going to make one part, I usually won't spend too long on the work holding. But if I want to reproduce it and make more than one, I'll spend more time, and that can be up to 50% of the time of making your first 2 or 3 parts is locking down your work holding. Once you have that repeatable, then you can go in and start cranking out parts, and most of the mill time, not that long.
Mm-hmm. We actually have someone in chat, or not someone, Deanna, who does a lot of CNC machining as well. And so I'd be curious to hear her comments. She says it differs from a 3D.
She's probably got far more experience than I did. So.
Yeah. She's saying that with the 3D printer, you change the settings primarily, where with CNC programming a part, you're going to choose tool paths and cutters and parameters a little more. And I guess that is something important that a lot of people don't consider with 3D printing, is the fact that not only are you much more free in terms of your design, but you're not restricted to using certain cutters or having to think about, okay, what radius bit do I have to do to get this particular feature? Because with the 3D printer, you're sort of, the nozzle is your primary constraint, and you can't print features that are less than the diameter of the nozzle. Whereas with the CNC machine, because it's subtractive, you might want to use a really big bit to cut out the bulk of your part and then switch to something smaller to do the finishing details. And then depending on what kind of crazy features you have in your machine, you might need like I don't know what those, like a milling bit to do flat surfaces, and then like a pointed bit to do really, really fine details. So I can imagine the design process is far more involved.
Right, and then you even have to vary the number of flutes per material you're cutting. So you could compare that to swapping out something like a tempered steel nozzle or hardened steel nozzle or ruby tip. Yeah. But really on your 3D printer, you set it and just tweak how much plastic you're squirting out at one time. Whereas with the CNC machine, one job may take 10 or 15 different tools, 10 or 15 cutters.
Yeah.
Right. There's also some considerations of like barrier to entry. Like if I just wanted to start up like CNC machine one part, I'd be very worried about, breaking an end mill or doing something that it looks good in the cam but the machine couldn't actually do. Like I feel like with 3D printing, you can just throw your part into a slicer and tell it to do its best and it will figure something out. Whereas with the CNC, you actually have to know what you're doing and understand the process.
I mean, you could compare that to overhangs with no support and they crash down on your bed.
Right. Yeah, I mean, there's still a little, you can go wrong with 3D printing for sure. I think there's maybe a few, it's a bit nicer when you fail with the 3D printer.
Yeah. Crash your nozzle into your vapor bed.
Yeah, that's not nice.
No fun.
We should show some of the metal parts that we've actually printed. Do you mind getting them, Steven, from the...
Yeah, I can get the Get some close-ups.
Well, we've got photos. I'll just show those.
Yeah, if you do, I think you'll have to go onto the drive for those.
Yeah, that's fine. But yeah, so I guess one of the main things we're talking about now is that, so 3D printing alleviates a lot of the design constraints. It alleviates a lot of the machine constraints as well, because you might want certain bits or a particular CNC machine. Dan was saying in chat actually that machining is defined usually by 3-axis, 4-axis, or 5-axis machining, and however many axes you have will really determine like what types of parts you can get and how many operations you can do without having to move the part around. Whereas with 3D printing, that's really not much of a concern. In fact, you can have internal voids in your part, which is impossible with any other type of manufacturing, right? So it's a completely sort of different way about thinking, or a different way of thinking about it. Just CNC is also a lot more dangerous. Yeah, if your tool heads shatter and you're not wearing glasses, yeah, it could be.
We'll talk about messy as well. I'm sure, Jeff, you probably have some chips flying around in your shop every once in a while.
If you don't have an enclosure, you have to be prepared with a broom.
Yeah, I bet.
It's actually, that's a good point too. Like the difference with CNC and something like, because what we should say is metal additive, at least the way that we've been looking at doing it, metal FDM, or it's sometimes called BMD, which is bound metal deposition, is the same essentially as plastic 3D printing in terms of the concept. So now the fact that you can produce metal parts with the same sort of design workflow as you would use for your plastic 3D prints opens up a lot of design freedom and actually a lot of potential cost savings for your shop as well.
Mm-hmm.
So like you said, there's not really a mess because you're doing additive versus doing subtractive manufacturing, and therefore you don't need like chip removal systems or coolant reclaiming systems, because the 3D printers don't generate chips.
Yeah.
They don't use coolant. You don't have to worry about keeping an inventory of extra tools in stock either in order to produce the specific part you need. And so that lowers either your inventory cost, like just for the machine itself, or it lowers your lead time. Like I don't know, have you ever run into the case where you wanted to machine something and then just didn't have the tool you needed?
Yeah, I mean, either you don't have the tool or maybe you don't have stock that's the right size, so you gotta order a big chunk of metal and wait on it to get to you.
Oh, that's actually a good consideration too. Like your metal block has to be big enough for the part you want to make.
Yeah.
So you can't just have, like with 3D printing, you just have a roll of filament or a box of material, and
you just use what you've got, and
yeah,
you probably have enough because it's on a roll.
That's interesting.
Right.
I hadn't even considered that.
Yeah. Well, say if you want to make like a really long and skinny part or whatever, then you'd have to have a really oddly shaped piece of stock material, unless you want to waste a lot of material getting, big block cut down. But yeah.
Yeah, and if you're into high volume, usually you'll collect your chips and either recycle them, or if you're really high volume, melt them back down into ingots.
So how does that generally work? In terms of recycling or waste disposal with things like CNC machining?
Usually clean chips that don't have any oil are worth the weight of the metal, but if they're covered in oil, you're not going to get much for them.
I know there's also like contamination considerations. Like if you've got a bin full of 99% aluminum and 1% steel, I don't think a lot of places would be too happy to take that. Is that?
Yeah, or a chunk of carbide that broke off in there somewhere.
Oh, right. Yeah. Actually, I imagine that would probably get pretty nasty for some of the recycling equipment. I guess it'd have protections in place to stop it from messing it up, but yeah.
So when calculating the cost,
Yeah.
oh, go ahead, Jeff.
Oh, I was just going to mention back to the 3D printing of metal.
Mm-hmm.
When you're building those parts, even if you do have to do some surface finish or hole tolerancing, those are going to be really light machine passes, and you're not going to have many chips and probably not going to damage your bits either.
Yeah, I imagine it's similar to like casting a part and then just finishing it off where you need those really tight tolerances.
Did we? I think we lost Jeff. Oh
He
no,
wasn't?
he's here.
No, he's here.
Sorry.
Yep.
We're just pulling up some images of our own metal printing because we've been talking a lot about it, but I think we need to show
Yeah, I think
show
people
off
wanna
what we've actually been doing.
actually see the
Yeah,
results.
I think you need to show it off too.
Yeah.
Okay, I'm gonna pull it up on stream. Why don't you guys continue talking about? Please buy me some time. I need
Yeah.
I need to pull up these images on stream.
That's okay. So one thing we've been doing is we've been looking at ways to automate metal using a desktop 3D printer. Because Quinley works on, you know, FDM printers that use, you know, filament, like fused fabrication technology, FFF or FDM. And there's a few options out there. So we initially looked at trying to use, so there's metal infused filament. We've been using UltraFuse 316L, which is, it's actually 80% stainless steel particles and then 20% plastic binder. And so this material, when you print it, it prints actually quite like plastic. And when you, after it's been printed and you sinter it, then all the plastic inside there burns away and the part shrinks slightly and leaves just the metal. So this is the sintering process. But one thing we found when we were doing this is that the UltraFuse was actually fusing to the vapor bed pretty well. It was having a hard time releasing. So we thought about ways to sort of get around that. And well, one solution that we found that actually does more than just allows release on vapor was using a dual extrusion printer. So what we have here is we've got two different materials in this in the print. So I don't know if it'll show up too well, but we have this stuff called what is it, polycast, right? This is from Polymaker, and we use this material as kind of an interface between the metal part and the bed. And what this does is it allows you to print on top of the vapor without you know, ultra fusing to the vapor, and you also get like a really nice surface to start your metal print on. So your first layer for your metal will be nice and smooth because it's printed on top of a raft. But then the secondary benefit of using this Polymaker is that it's actually also just a really good support material in general. And when using like metal FDM, it's really hard to get you know, supported features without using a secondary material, because if you try to support metal with metal, then they'll fuse together.
Yeah.
And you'll have a really hard time finishing off that part.
That's actually a really big problem in metal printing in general, because sometimes you'll even use supports in like the powdered based ones, because those parts warp as well. But especially with metal FDM, and I'm just gonna switch to some photos of it so that we can look at it up close. But what I discovered was that, or the original reason I wanted to use the polycast is it's a casting filament, which means it was designed to you would print your part entirely in that filament, encase it in something like casting sand, and then pour molten metal to replace it. So it's like a lost wax casting analog material. And the whole point of the material is that when the molten metal hits it, it burns away and it produces very, very little residue. And so the reason I thought this was really useful is, well, you hit the temperatures required for polycast or wax to evaporate in a sintering oven. And so what I thought would be an interesting idea is, well, what if we printed all the supports or the support interfaces out of this polycast material and see whether we could get an interface that supports the part while it's printing, and so you can get really nice bridges. But when you actually go and sinter the part afterwards, it'll, essentially evaporate away and leave a gap between the supports and the part, making it really, really easy to remove the supports afterwards. And there are similar technologies or solutions that is what inspired this, that have been used for metal FDM. So one of the big ones that companies like Repedia and Desktop Metal use is a ceramic paste or bound ceramic. And what they'll do is they'll print an interface layer out of that ceramic stuff, and then that ceramic turns into dust after it's been sintered. What we're doing with this is the actual support material will completely evaporate after it's been sintered.
Yeah, I believe that the stat on that is actually 0.003 of the polycast is left once you burn it. It'll be left as ash.
Yeah.
So that's like 99.97, 997. A lot of it is completely evaporated.
Basically no residue will be left.
Yeah, it's good stuff.
After you sinter it, which is really cool, and it's really useful for removing those supports, because with the current, like the state of the art right now, and I'll pull up a video. Is these separable supports. Let's see if I can find a video. They are still very difficult to remove, and it kind of makes it inaccessible because you'll need special tools to remove them. So I think the video is visible on stream. I just want to make sure that
No, we're covering it.
we're covering it a little bit, but you
Not
can
the important part.
This is sort of like what's used in metal FDM right now. It's a ceramic supports. You can see the white.
It's just the interface layer, interestingly.
Well, I think that's how we would have to do it too.
Oh, you can't use the polycast itself as support?
Because it needs to still be there. And here's what happens, right? You end up with a lot of ceramic powder that you have to clean up afterwards. And you still need to use tools to get the supports out. Whereas this stuff literally becomes ash, and so you're not going to have to deal with this post-processing mess. And I think, that will make automated bulk processing of these metal 3D prints much, much more simple to do.
Yeah, like you won't have to clean dust off all the time. You'll just have cleaner metal parts.
You can literally just throw them in the oven and there will be no post-processing required. The only thing that we still have to experiment with. So what I'd done was I tested metal supports with a polycast interface.
Yeah.
The reason for that is the supports still need to be there during sintering.
Mm-hmm.
If it was completely polycast, they might evaporate at a too low temperature and then the part will just sag.
Right.
But I don't know, it might be possible to do them completely out of polycast and have the entire support disappear during sintering.
Yeah, well, I'm just wondering if the part is already printed, does it still need support during sintering, or is it more that it needs to be supported during the print process?
Typically, it depends. It depends so much on the sintering setup, and it depends on the length of the bridge. So if you have a really long bridge, I don't know, 15 centimeters,
mm-hmm.
It's possible that it will sag during sintering. So you would want a metal support there. But the nice thing about, and this is something I tested, was the with the evaporative interface, the top metal part doesn't fuse to what would be the metal supports.
Right, there's an air gap.
There's an air gap, and they don't really like fuse to one another, which is what's important, or the whole point of it, having the interface like that. So that was like a really exciting discovery, because it means you can now do really, really simple bulk post-processing where you don't have to have this like powder management you saw in the video. There's so much powder and you have to knock all these tiny metal parts loose. You won't have to worry about that stuff anymore, which is really, I think is going to be a really big step, because even though we can automate metals, we also have to think about the downstream processes. Like, okay, how do these parts actually get processed afterwards?
Well, that's another important thing about like powder bed printing, is you get all these parts off the printer and they're full of powder, because the whole bed is completely full of powder. And so even if it's got holes or cavities, then you've got to remove that powder somehow. And that's more or less a manual process. They've got like automated like vibrating machines or whatever that can get rid of that powder better, but it's still like an additional step.
And the problem with that, as with everything in 3D printing, is you don't know what part is coming out of the machine. And your system has to be able to work around any part. So the fact that these just work by throwing them in heat, like heat is pretty shape agnostic. It doesn't matter what part you're heating up. As long as there's heat there, the supports will disappear correctly. I'm just throwing up some video, some photos of the different metal parts we were printing. There's one on the altar.
Yeah, I've noticed in some of your previous videos that you talked a lot about the post-processing of 3D printed parts. And I've picked up a lot of that advice, and it does make a huge difference if it only takes you a few minutes to snap off a bed skirt versus having to use a knife to cut down a bunch of extra parts.
Here's something, actually, we'll show it on stream. That's really cool as well. So Steven had mentioned earlier, and I'll just pull up a better photo of it, but for it to work with the vapor correctly, we do print on a small raft. I'm just trying to find a good example of it. Oh, here. Okay. So you can see there's this polycast raft. I guess, Jeff, you can't see. You might see it on the stream in a sec. There's a polycast raft underneath the part, and the vapor bed can work really well with the polycast. But the really nice thing about it is you can just peel it right off with your fingers. I just want to make sure it's visible on camera.
Let me get one shot of this.
Like the TPU printing.
Yeah, exactly. Like you can just peel it right off without any tools. I don't know if you saw that the desktop metal video we were showing, but there was a lot of prying going on. But this you can just do by your hand, and it when everything cools down, this comes off extremely easily. So I can't imagine it would be too difficult to come up with some kind of automated process to remove these, or which I've tested, is you just throw this into the sintering oven with the part, and the raft will evaporate, and then you don't even have to worry about it or change your process very much. So yeah, like it definitely makes metal FDM extremely accessible to like you don't need very much special equipment, and in fact we're mainly planning to recommend this to be just printed on Ultimaker S5s, because they've got really good dual extrusion, and they're extremely capable machines, and they actually work well with the metal. I think Ultimaker and BASF have done. There are profiles for the BASF metal materials in Cura, so they've clearly worked together on making sure that the machine was compatible with it. And a lot of places like already use like more professional settings already use Ultimaker S5. So it wouldn't really be that much of a jump or a modification to just say, hey, we've got Quinley for Ultimaker, it can do plastic parts, and now we've got this version of Quinley. You can use the same machine and print plastic or print metal, and you don't have to change any of your processes. You don't have to, and you don't have to hire somebody to post-process every single metal part that you get.
Yeah. Well, I think it's also worth mentioning that the Ultimakers are very, like the skill barrier for using an Ultimaker is quite low. Like they do a lot of things in order to make it quite plug and play. So you don't have to have, you know, a 3D additive specialist to get metal parts printed now. Um, you know, if you've got someone in your company who knows how to 3D print plastic parts, a lot of those skills carry directly over to metal.
Well, actually,
So you're gonna print your Ultimaker Quinley kit out of metal?
that's a good question.
Should we? Is it necessary?
Maybe some parts.
We do print a lot of parts in the Ultimaker kit, and right now they're a silver color, which kind of looks like metal. I don't see a need for actually doing a lot of these parts in metal since the loads are quite low. But
Yeah,
maybe we could do one as a
as a proof of
as a
concept.
proof. Yeah.
I think it's mainly none of the parts should be heavy in our system.
Yeah, like the opposite. Yeah, we actually like
Yeah,
having
kinda
things light.
Going for a really light system. I wonder, maybe we could do like, what would we even do out of metal on?
Question for chat.
Yeah, question for chat.
What
Good
should we print
question.
out of metal?
Oh, Polymaker's actually in chat. That's pretty cool.
Polymakers in the chat. Hello, Polymaker.
Okay, I'll play them a specific video. I'll play them a close-up video that I've taken of the Polycast in use. It's actually really, really cool. And you can check it out on stream too, Jeff, if you want. Just 1 second. I'm gonna have to switch back to this and then find the video.
What's Polymaker saying?
They saw our Polymaker raft.
Ah.
And I'll show them.
I'm curious if they've seen other people try something like this with their
I don't think
podcasts.
it's ever been mixed with metal FDM before, so that's
Interesting.
very curious. I will show them the video because I've got a nice video of it too.
Did they see us removing it?
Yes.
Ah.
Okay, here, metal parts footage. Oh, the quality is not excellent. Okay.
This is a heat exchanger, fully metal 3D printed. Quite an interesting design.
Yes, and it's printed actually with, there's a really interesting, it's got like a helical cavity inside. So when you run whatever liquid through it, the stainless, it wraps around 3 times in this heat sink. So here's an example of this. That bottom raft is the Polycast, and then this is the BASF 316L stainless material. And what's actually really nice about this, unlike regular 3D printed supports, you can mash. It's kind of, it shows for a split second, but you can mash this metal filament right into the Polycast, and it will still separate, like it won't fuse. And so you can get really, really clean, flat bottom surfaces, which is not very common with support.
Yeah, well, usually when you print on a raft, you have like a set air gap value.
Yeah.
Whereas for this, you could probably get away with 0.
I was actually using a negative air gap.
Oh, super mashing into it.
In this part, it was a negative air gap just because I wanted to see like whether or not it would fuse with the Polycast, and it doesn't, which is awesome.
That's
because
good.
then you can have actually like dimensionally correct overhangs and bottom surfaces which
Mhm.
you would typically, like, those are the poorest tolerance parts of a 3D print. So the fact that you can actually have material on material contact um, means that you can have much more accurate parts coming out.
Well, that's great because a lot of people use a raft in order to get around like the elephant's foot issue, or I guess even the inverted elephant's foot issue, which is when you like print too high on the first layer.
Yeah.
But for this, your printer knows exactly where it is in space because it just did the raft. So um, that should be great for getting a really good high tolerance first layer.
Justin's got some.
And you don't have to worry about your bed level either.
Yeah, that's true.
Yes.
Yeah, it gives you a lot more flexibility. And actually, the Ultimakers are really nice. They have a nice auto leveling system built in.
Yeah.
It uses the nozzle itself pushes into the bed slightly, and it measures the point where the distance from the sensor to the bed stops changing. It's a really interesting way.
Yeah, it's pretty cool. And yeah, that's why, as you can tell, we're very excited about this because the prospect of being able to print like competitive metal parts on, you know, a $10,000 to $15,000 machine is really exciting. And then some of the other interesting things are when you look at, like, okay, so what's the actual cost of these parts compared to state-of-the-art things like CNC or metal injection molding. And so yeah, we've talked a lot about here's how we got the metal to work with automation, and we're doing great parts with just normal FDM printers that are enabled by Quinley.
But was it worth it?
Yeah, is it
Can
worth
you,
it? Like,
does it mean anything?
can you actually use these parts? And so we'll be putting out, well, we put out a press release this
Literally today and
morning.
tomorrow.
Yeah, and then there's a metal white paper coming out where we delve into like material cost and machine cost and some of the key things, like the key takeaways that we found was with an automated system using BASF's like current library of materials and the polycast, we were able to get the bound metal deposition parts, so parts that are printed with this style, about 67% lower cost than the competitors.
On a per part metric.
Per part.
So these cost 67% less than what you could do with like a huge $1 million machine.
Yeah.
$2 million machine.
Yeah. So that's one thing. On a per part basis, this is much lower cost. And those are much lower cost. The machines out there right now are typically much lower cost than CNC machining. But the really interesting thing is again this lowering the barrier to entry for metals, where we found that so typically on a binder jetting machine, and we've done exact comparisons in the white paper, but you could have a let's say, for example, there's a part where the published numbers for the throughput is this machine can make something like 56,000 of these parts per year. And so we looked at, well, how many Ultimakers with Quinley would you need to make 56,000 parts per year with metal FDM? And it turns out that in this example, it was you'd need 14 Quinleys, but even though you're setting up 14 Ultimakers with Quinley, the cost is 90% lower. It's a 90% lower capital expenditure as compared to one of these binder jetting systems. And the best part is you're equal in throughput. And not only are you equal, but the Ultimaker with Quinley is completely automated. So you're actually requiring less skilled labor and less training to get up and running. As long as somebody knows how to print plastic parts on an Ultimaker, which is already very easy to do, they'll be able to switch over to doing full-scale metal automation within a couple of days. And that's like completely completely different from when people are looking to invest in a massive binder jetting machine or system where you have to consider things like large amounts of floor space, what area are you going to dedicate to doing this, where are all the materials going to go, who's going to be running the machine, do you have to train them, do you have to hire someone, or do you have to contract some kind of service that does the maintenance. Whereas with Ultimakers, a lot of these smaller machine shops and companies have them in-house already. They've been using them, so it's not a new system to them. And the Ultimakers are already really easy to use, so you don't have to even think about really hiring someone that knows everything about metal 3D printing and somebody that's highly skilled just to do this one thing.
It's a lot of benefits. I mean,
Yeah.
what we covered there was like your initial cost is 10 times less. Your parts are almost 3 times cheaper. Your skill level required is a lot lower. The amount of labor required is a lot lower. Like there's a lot of benefits here. You know, it's hard to think about right now because it's just in the beginning, but I think it's going to be like a pretty big deal when we actually get this rolled out.
And just yeah, I'm curious to hear your thoughts, Jeff.
I'm trying to figure out where I'm going to put one.
Yeah, there's a bit of an information dump.
Yeah, have you ever like looked into metal additive, or has it always just been kind of like something interesting to think about?
From a business perspective, it's always kind of been out of reach because of the cost.
Right.
But this looks like it could really be something that could work on a business of my scale, which is not doing, I don't need to do 57,000 parts a year, right? I might need to do 1,000 parts.
Yeah, even I mean, it is the nice thing is you can just get one machine and run it 24/7 with Quinley, and your part cost, you're not gonna like your part cost will be the same whether you're running one or whether you're running 100, unlike with these huge systems where the part cost only goes down when you buy a bigger printer.
Or when you start running, you know, hundreds of parts on like a very optimized CNC fixture toolpath combo.
Yeah.
Yeah, having a fixed cost per part makes like a lot of things easier, and it's usually cheaper, at least from the numbers I've been looking at. Until you do huge production runs where, you know, injection molding actually becomes feasible.
And by huge, we're talking, you know, hundreds of thousands right now, which is not a number common to 3D printing. It is more common in binder jetting for both metals and polymers, but most of the stuff out there is you're only looking at doing hundreds of thousands if you're printing, you know, minuscule, tiny little parts.
Because you could probably fit thousands into a build volume on these massive industrial printers. Like some of these printers take up like 100 square feet space, and they have huge build volumes. I don't know how long the prints take. Like
they're pretty fast sometimes.
I know they're fast. So 14 Quinleys equals one huge production system.
Yeah.
You know, but it does take up a lot of space, and you know,
there's all the post-processing.
Well, 14 Quinleys also gives you a lot of flexibility, right? If you've got one binder jet running a job, you've got to wait till it's finished before you can start anything else.
That's
You've
true.
got 14 individual Ultimakers, you can take one off the line and switch it to doing something else.
Yeah, that's the nice flexibility too. Actually, I see that. So you've got like shelves right now set up with your the Quinleys. What we looked at was sort of like the floor space that would get taken up by 14 Ultimakers versus one huge powder bed printer. And so it turns out if you stack the Ultimakers too high, so you get one on top, one on bottom, and you use just like a shelving system, it's only about 30 square feet of space. Um, so it's like 3 feet this way, 10 feet that way. It's just a wall basically.
Do you know how big the powder bed system was?
About 100 square feet.
So it's 3 times more dense.
3 times more floor space. It doesn't
Yeah,
go
yeah.
as high, but it's 3 times more floor space.
Okay, so wow, that's pretty. I didn't know it was that much more floor space.
Yeah.
So you could make the same quantity of parts in 3 times less floor space using the Ultimakers and the Quinleys.
Yeah.
Okay.
So in terms of like
That's pretty crazy.
parts per square meter,
Yeah,
we're 3 times more dense.
that's ridiculous.
I love looking at all these interesting metrics that you can pull
Yeah.
out from running the numbers.
One of the ones I was looking at was for equivalent spend. So if you were gonna spend $2.5 million on a binder jetting system, or if you're gonna spend $2.5 million on just Ultimakers and Quinleys and BASF and Polycast,
Yeah.
you would make it was a benchmark part. It was the same part being printed on both systems. You could make on the binder jetting system 62,000 a year, I think. Yes, it
I
was.
want to say 60 something, and then we had 700 something on the Quinleys.
Yeah, so I think it's 62,000 per year of this part on the 100 square foot binder jetting system. And now with $2.5 million, you can buy about 140 Ultimakers. But for the same spend, you would be able to produce 711,000 parts per year.
That's a lot of parts.
And the parts would cost much less, which is the really important part, which is now you're looking at metal FDM competing with things like casting and with things like metal injection molding. And that's a scenario where you're probably not going to want to use metal FDM for 700,000 of the same part per year. But consider now that you can do 700,000 of completely unique parts.
Yeah, so assume you've got an inventory of 100 different metal FDM parts. Now you can set like 2 printers can do that, 1 printer can do this.
Yeah.
And then just loop them and let them go.
And there's no way that casting or metal injection molding will be able to compete on that front, because you would be paying for, in your scenario, you'd be paying for 100 different tools.
Yeah, well, they could only run one part at a time.
Yeah.
So you'd have to be telling them to do a production run of 100 of these, swap it out, 100 of these, swap it out.
So it's
a lot of actual labor goes into that.
Yeah, it's really exciting actually being able to take all these benefits from plastic FDM and bring them over to metal. The other really cool thing about metal FDM, because it's not used very much right now, and a lot of people have concerns about part strength, but it turns out that metal FDM, binder jetting, and metal injection molding all produce parts that are the same strength and hardness.
Yeah.
At least for stainless, right?
For stainless, yeah. The only consideration is that in the Z direction, it's 10% weaker.
Yeah.
So 10% is not a huge amount, right? In a lot of plastic FDM, it's closer to 50, maybe even 60% weaker. With metal, it's only 10.
I think it bears reiterating, when you're actually switching over to 3D printing for production, you're not going to be comparing parts on a one-to-one basis. 3D printing gives you the extra design flexibility to be able to compensate for that slight difference in part strength. So if metal FDM, is 10% weaker but costs 67% less, you can make a design that reinforces that part by 10%, and you'll still be saving quite a lot.
Mm-hmm.
So I think that's an important design thing that, or consideration, that when people are doing these comparisons, you really shouldn't be comparing them one to one, because the approach you take to designing the part is completely different. How would you say, Jeff, that when designing something for CNC versus for 3D printing, like how did that change the way you thought about like the construction of a part?
Well, the biggest constraint when you're seeing if you're on a 3-axis machine is everything's top down. So you can flip your part and do another operation, but that takes time. So a lot of your designs are based around the limitations of your machine, like Deanna was saying. If you've got a 4 or 5-axis machine, you can do a lot more operations without having to refixture your workpiece. Whereas with a 3D printer, your limitations are going to be in overhangs and supports and material strength, so you can't have too thin of walls.
Yeah.
Really, when you're looking at those two limitations, it's based on the time investment you're going to have to do making the part with a CNC machine versus with the 3D printer. When it's automated, that kind of goes out the window, right? You get these Quinley systems, and once you've got your design locked in, you just keep them going. So if you're doing 3D printed metal parts, those constraints you have from your CNC machine axes are not in play anymore. You just keep cranking out these parts over and over, and then put them in your centering machine.
Yeah, well, that's a good point. Like having like a sort of a continuous production process, you can optimize while you're producing. So, with plastic parts, you're not going to get the first one to be perfect. But that's why you optimize and dial in G code. So I'm assuming with the metal parts, it'll be a similar process where you'll have to do a few iterations, but you can get away with that because it's 3D printing. And being able to have like that design flexibility, it'll just make you finish your project or finish your parts faster. Yeah, so
Right, and it's a 3D printer, so if you want to do quicker prototypes, you do them in all plastic. Then when you're a few iterations in, you switch to metal, because that's where your bigger cost of iteration is.
Yeah.
right.
I was actually going to ask you that, because that just made me think of something. The fact that you're doing both on the same machine means that you could just iterate in plastic and then switch over to metal, and you know that the part design will be 3D printable.
Mm-hmm.
Because the metal FDM,
Exactly.
at least the stainless, it's actually not that different from plastic. I actually started with one of my PLA profiles to print this stuff, and just adjusted, I just adjusted the temperature and the extrusion width, and I just slowed down the speed. But the fact that you can use an identical system to do your prototypes as your full-scale production, we've already seen that in plastics. It's super useful.
Mm-hmm.
But now for metals, the fact that you can have an exact plastic analog, same tool path and everything, and just switch to metal when it's ready, I think it will be, it's kind of hard to guess how much time that would save people, but I can imagine it's quite a lot. And one thing I did want to ask you, and maybe Diana, if she's still in the chat, is when machining, do you ever do like a plastic prototype with Delrin or something first, just to make sure the tool paths are correct, or do you just kind of have to sacrifice a piece of metal?
Personally, I don't usually mill plastic. It makes too big of a mess, and your feeds and speeds are going to be off. So
You just do it in one shot.
usually just hope you get it right and run the simulation a bunch of times.
Right, yeah, because like one G-code move that's wrong could mess you up.
Oh, right.
I've seen people do it in
So
foam,
you
for
don't
example.
set your surface height right, and your bit starts moving across and gets hooked up in a
Hmm.
hole.
I guess one thing, I have seen people use foam to do proof of concept, I guess. Um, I don't know if they do that in like production environments, but um, yeah, like just in at my university, I've seen it a couple of times.
Diana says in chat, she says, you basically just have to be good enough
You just need to go for
to
it and
trust your tool paths.
be good.
Okay, so she would program and then baby step the first one.
Right, so that's when you can probably just go through G-code commands one by one. Keep one hand on the emergency
Sure.
stop.
You know, you run your air path, so you
Right.
set your Z
Oh yeah,
a couple inches higher than your workpiece and run your air paths and see if everything feels right.
gotcha.
That sounds like a pain.
Yeah, well,
I'm
I
very
did this for a
non-.
little bit. I did like a 1 year thing where I did a bit of CNC machining, and there was at one point my boss basically was like, just keep your hand on the emergency stop, and if it starts going bad, just whack it. It's not what you want to be doing when.
Polymakers exiting the chat. Thanks so much for joining us. Your material is really cool, and I'm glad we were able to use it in this application.
Yeah, it's great to see Polymaker here. Hope to see you in a future stream.
Yeah. Diana does not run an air pass. She's just that good, I guess.
Wow.
But
This
that,
is like someone running their print and then not watching the first layer.
I do that.
I do that too.
I do that all the time. The risk is so much lower.
That's a really great comparison.
I mean, anyone using Quinly has done that now dozens of times because
You must have
they
had to.
run it overnight. Yeah.
Yeah.
That's
Not the typical
yeah,
programmer.
she's got the
Flexing.
skills. But that's actually a good point. Like, it's uh, it's a bit tangential, but the fact that you need so much experience and skill to operate these machines, it's also an issue in 3D printing. And I think I mentioned this last stream, but I had done some calculations on how many operators would be required to run all the 3D printers in the world, like this year, next year, the year after, and so on. And right now, there are 4.2 million 3D printers out there. Just they weren't all sold this year. They're kind of from the last 3 or so years, and it just assumes like a general 3-year lifespan for 3D printers.
Mhm.
And it turns out if you wanted to run them all 24/7, you would need 1.2 million people, which doesn't seem that unreasonable right now. Like you need 1.2 skilled operators and know how to use a 3D printer. There's definitely that many people out there using 3D printers and able to run them. But then when you start looking at the market projections for the 3D printing space over the next 10 years, the number of labor required starts getting really ridiculous. So in 2025, so in 4 years, it's estimated that there will be about, I think, 18.2 million printers out there.
So 4 times more than we've got right now.
4 times more in the next 4 years. Yeah.
Yeah, it's following like the CPU processor speed rule. It doubles every 2 years.
Yeah. But the problem is the amount of labor also quadruples, and you'll need 4.5 million people to run that many machines. And like, where are you going to get, where are you going to get just over 3 additional million people educated enough to be able to run these machines 24/7?
Yeah, they're gonna have to do a lot more 3D printing in universities in the next few years.
Yeah.
Which they are. Actually, Eric, one of our favorite people, has been doing that.
And that's still, that like 4.5 is still pretty reasonable, but it is like the industry would have to grow by an insane amount because paying the wage of 4.5 million people is like a lot. It's very expensive. So the industry would have to be bringing in, I think it's like $200 billion a year in order to pay all these people.
Right.
Or a lot of them are going to be hobbyists that work for free, right? That are not getting paid to use their 3D printers.
But they also tend to have like one printer or two printers.
Yeah.
So.
But does that mean that the industry, that most 3D printers in the future are not going to be used in industry and not going to be producing? Are they all just going to be going to hobbyists who don't need to get paid to use their 3D printers? Like,
well, that's a good question. Do all the people who want 3D printers already have one, or is there going to be an ongoing need for more and more 3D printers?
So it's an interesting problem, and I think what it points to is the fact that 3D printers, as they are now, are too difficult to use or require too much labor, which is where I think automation technology really has the opportunity to shine, because I think it's somewhat unreasonable to expect a labor force of 4.5 million people to just appear out of thin air in the next 4 years.
Mm-hmm.
And if on the flip side, in 2025, if every single one of those 18 million printers was running a Quinley, the labor force required to run them 24/7 would only be 40,000, which is
how many printers per person?
It's like 70 to 100 printers per person.
Right. So we have one person in charge of a Quinley print farm.
Yeah, roughly.
Yeah. Large proportions. That's the future.
Well, and that's based off of the numbers that Eric Woolridge gave us from the University of Kentucky. So he actually did a study on how much time does it take to use Quinley machines versus how much time does it take to use just a normal manual machines, and that's how I got those numbers. Where
like how many Quinleys could a person reasonably do in a 40-hour work week?
Now here's the other thing too. All of these studies, all these like market projections, they estimate 100 million FDM 3D printers by 2030.
100 million.
Yeah.
That's really following the doubling rule.
It's kind of insane, and there has to be some kind of change in how 3D printing works if we're ever going to fathom running 100 million 3D printers.
Yeah, I just want to think about how many.
The quality of extruders has got to change a lot to get 100 million 3D printers out.
Yeah, there's a lot that it will take to get there. Like the things will have to not fail as often as they do. And
yeah, I can't imagine there would be like 100 million scraping things that need to be done every time. Like that's archaic for us anyway.
Even if they were only printing one part a day, right?
Mm-hmm.
That's 100 million. That'd be 36 billion parts per year, and 36 billion scrapes per year.
So 6 billion scrapes. Think about how many things could be done. 36 billion scrapes. Think about how many things could be done in 36 billion scrapes worth of time.
Yeah,
that's like human lifetimes of time. Like
yeah, like that's why either
these numbers are getting big, so it's hard to come up with estimates. But
yeah, it points to
how many human lifetimes of scraping are we setting ourselves up for if we don't move toward automation?
Kevin also points out, and it is one of the things, like how many of those 100 million will actually be running, which is a good point. How many of the 4 million are actually running that are out there right now,
and how many are just collecting dust?
Yeah. It like I said, it either points to the market projection is completely wrong. Most of the printers won't be printing. Most of the printers are going to be hobbyist machines that no one gets paid to run. Or 3D printing is going to have to get a whole lot more easy for people to use, in the sense that one person will have to be able to manage a fleet of a few hundred machines.
Yeah, I think it's the fourth one probably.
I hope so.
That seems to be a good one.
That's the whole point of our 3DQ.
Yeah.
But yeah, it's kind of it is an interesting thing that I've noticed, because these numbers are everywhere in industry publications, and yeah, it points to us hitting a roadblock somewhere, and hopefully Quinley can help solve that roadblock.
I do believe we are approaching the
And
end.
I didn't point this out earlier, but one of my machines behind me had a failure. I think it goes to really drive in your point. The failure's not in the bed, it's in the extruder or the filament or the drive motors, right? So
Oh, really?
I've got 3 printers back here, and in the past 24 hours, I've had 2 failures.
And
Yeah.
it's like, yeah. What do you find now the most common issue you run into when you're running them this hard?
Quality of filament is really critical. If your filament diameter varies across a spool, if the spool isn't wound properly or not round, it really causes a lot of issues.
I think that's probably what we see on
Right,
our.
because you're slicing. Once you slice something, it's set. If you want to print 50 of them, and there's a variance from the start to end of your spool, your last parts are not going to come out.
Yeah.
Yeah, like we've seen the similar thing when you get bad filament, it just ruins your reliability more than any other like variable, really.
We've had to throw out entire batches of parts because we got filament that did not behave correctly. Like we recently got a batch of PET-G that melted at a lower temperature than our PLA. Like
It was like deforming at like 50 degrees.
it was
It's bizarre.
we had shipped it was a Prusa beta kit. So before we had started shipping the Quinleys to everyone, that was printed in that material, and it literally just melted in the heat of the post. And PET-G, it should start to soften at 60 or 75 degrees. The fact that it had completely warped in the post is insane to me. And then we did a test where we had like the same part in PET-G and PLA, and yeah, like the PET-G that we got was completely molten. And the worst part, and I think this is something that the industry will have to reconcile in the next couple of years if it wants 3D printing to be more mainstream, is the material, like the material standards for FDM have to get a whole lot better. There needs to be more transparent about things like composition, or at least material properties, because the fact that we buy PET-G from 3 different suppliers and one of them gives us something that's like weaker than, or a lower melting point than PLA, and they're all labeled PET-G, it's pretty unacceptable. And as you said, it's probably one of the biggest things we face on production is just inconsistent material quality and not knowing how a material will behave until we buy it, or a material suddenly changing on us. Because we actually, that PET-G we did buy, we had used the same brand a few months prior and it worked perfectly fine. And then we got 10 kilos of it that was just, I mean, it's essentially unusable. Like imagine you're machining stainless steel parts and 1 in 10 of your stainless blocks are suddenly aluminum. Like it's literally like that. That would be pretty unacceptable.
Pretty bad.
Well, and part quality is not the only thing you have to worry about with material composition. If you're printing indoors, which most people are, you've got to worry about indoor air quality and chemical release and toxins. And if there's no transparency in the materials, you don't know what's going into your air.
Yeah. And there are now, like, because I think we're sort of seeing in materials, I think it happened in materials first, but it was kind of a thing where just in 3D printing and the industry in general, it's sort of everyone started out as a hobbyist, and so a lot of bad habits kind of carried in as things scaled up. But now you're seeing like actual proper materials and chemicals companies producing very high quality, very consistent filament. And I think things will improve. And I mean, they have to improve in order for production to happen. And we actually, you hear now a lot about companies that had been producing plastics for other industries are now getting into producing plastics for 3D printing. So they got all the expertise of calibrating certain materials for other applications and are able to transfer that to 3D printing as well, and like the same processes and quality control stuff, which is why we work with Mitsubishi Chemical America, because they have that kind of like really robust system, and we can generally we can trust them that they'll give us the same material every time, versus someone fairly new. And actually, it makes it much more difficult for newcomers, because now you don't know whether like this new filament store that's making it themselves, you don't know what their plastics expertise are, and you kind of have to take a risk. Oftentimes we find we buy one spool of filament, test it, and then only if that's good, then we go and consider actually using it for production. It'd be nice not to have to do that, but you don't know what's really in the plastic.
Yeah, so that's, I guess, a good point. If you're having filament issues, it could be worth going for like a known, trusted brand rather than finding the cheapest no-name thing on Amazon.
That will just give you a bad time, always. And honestly, Amazon is not even the lowest cost stuff out there now either.
No, you can get really bulk
it's ridiculous.
supplies. There's deals as well that go up, and I haven't actually tried any of those. Like some of the rolls go down to like $7-8 a roll. I don't know, maybe they're that cheap for a reason.
Yeah, they're like 90% plasticizers. They're not even like PLA or
10%
whatever.
PLA.
Yeah. That's the thing.
It's hard to know.
There's no standards in the industry. Which
and then some of it's probably great, and you just have no way of telling.
Yeah.
So it's hard.
Yeah. It makes it just ruins it for everyone. It ruins it for new innovative materials companies, and it ruins it for everyone that's trying to use 3D printing in a serious way and doesn't have time to reslice every single part whenever they buy a new roll of filament. Yeah. That's kind of tangential, but
just let us go off on our filament rant for a little bit.
I mean, it applies to metal 3DP too.
Yeah.
One thing I would really like to see is right now for the BASF parts, you have to send them to their service to sinter, because there isn't very much information about it. But I know they had talked about doing that it was like an open material system. At least in the past, they had some communication around that. So I'd really like to see.
I've seen that recently too.
Yeah, you have?
Yeah, just researching yesterday.
Perfect.
Yeah.
Yeah, I really hope that they start putting out more numbers about how individuals, or not individuals, but smaller outfits would be able to process these parts, because that's going to be really really critical.
Well, it would be good to have standard sintering temperatures and times, and possibly curves depending on the quality of your sintering machine.
The other thing is that depends on the sintering oven too, which is I don't know if BASF's ever going to sell their own sintering oven, but yeah, it's going to be interesting to see as this hits higher and higher volumes.
Yeah. Still a lot to think about, but yeah, we covered a lot of ground on this stream.
Super exciting.
Yeah.
Metals on plastic 3D printers.
Wow. And polycast, whatever that is. Partially plastic anyway.
It's a polymer.
Polymer. Cool.
Well,
hopefully we've shown that additive metal can be done on a Quinley system at a very, very cost-effective and good quality rate. So,
yeah, that's exciting stuff. You guys have really been cranking out the new ideas as fast as anybody can keep up with them.
Thanks. Yeah, it's been a idea for a little bit, but finally got to start working on it a few months ago, and it's been, yeah, the results have been awesome. I think, well, everyone should keep an eye out for the white paper coming out that goes into more of the business side of things and the actual costing, but it's very exciting to be able to say that metal 3D printing is a, or high volume metal 3D printing is a possibility on the horizon, and the barrier to entry is going to be it's going to be dropped by an order of magnitude, which is also really exciting. I think the more of these tools we can get into the hands of more people, just the better that the better parts we'll see, and actually, like, just in general, everyone in the world is going to have better designed products, lower cost products produced locally. Yeah, that's what I'm excited for. I want to see 3D printed products out there.
We're looking to make 3D printing part of the better future.
Yeah,
We hope to, yeah, make that possible.
I gotta thank you again, Jeff, for joining us and lending us your insight, and yeah, and it's awesome being able
Well,
to
thank
see
you for
using-
having me. It's been really great to talk with you and share ideas, and you guys have inspired me to maybe expand my business a little bit.
Yeah, well, it's great hearing your perspective on both the 3D printing side and the CNC side. It's a good combination of skills, and yeah, it's very nice to hear what you had to say about what you've been doing and what we've been doing.
Yeah, I'm excited to see where you take this. I'm just gonna put up the images again, and
We should also plug Machine
Yeah.
Creators a little bit here.
I was gonna say we should mention your Etsy store where people can find these products that you are printing on Quinley.
Well, actually, in the description, we've got a few links to the Machine Creators store, and also his Twitter and YouTube. And he actually sells his own version of our Quinley kit for the Voxelab Aquila on his website. So that's really cool. Go check it out. Give his YouTube channel a subscribe. Follow his Twitter.
Yeah, I've got a Quinley Voxel Lab assembly video coming within the next week or two.
Oh, that's awesome.
That's cool.
Yeah, that's gonna be really, really helpful.
And send that to us because
Start to
we'll share it
finish, firmware and bed leveling.
That's awesome. Yeah, I look forward to checking that out. And I think a lot of people in our Discord will be interested as well.
Yeah, especially those with the Ender V2, they'll be able to use a very like probably most of the steps as well.
True. Yeah.
At least for the firmware, because it's so similar.
Yeah, it's pretty much the same.
That's awesome. Yeah, I'm really looking forward to that video, and yeah, definitely go head over to his store, check it out. You can probably get better shipping rates from him than from us too, which is good to keep in mind.
I actually don't have any of the Quinley kits listed on there. I've sold them all or used them. I got to get some more from you guys.
Okay.
Ooh.
Well,
We'll talk to the management.
Management.
Mateo's kind of the management.
Yeah,
So,
and Steven is the product lead, so
we'll talk to each other about it.
we'll talk to each other after this stream. But that's awesome to hear that you got them all out there. Yeah, well, thank you so much. It's a pleasure as always talking to you and hearing from you, and hopefully everyone watching learned something, and I hope everyone's as excited for us about the prospect of high volume metal additive. I think it's going to be a really exciting future.
Yeah, I'm looking forward to it. Thank you, Jeff. Nice talking to you.
Thank you.
All right, we're signing off.